So what is this thing called the Fourier series, and what is frequency domain analysis? So the Fourier series is used when we are trying to analyze signals in the time domain that are periodic. We're going to look at non-periodic signals later, but for now we're going to concentrate on periodic signals. So how do we do a periodic signal approximation? Well, let's consider a typical periodic signal. So here we have a binary pulse train, and it's got some defined period, t0. What do we know about periodic signals? Well, by definition, a periodic signal is one that repeats itself every t0, or every integer multiple of t0, where t0 is the fundamental period, and there's a fundamental frequency f0, which is associated with that. The fundamental periodic signals that we want to use as our basis functions are sinusoids. So we know that there's cosine and sine, or we could use the phasor form, e to the j omega naught t, and just want to draw your attention back to Euler's formula that those are actually linked together. So we can use one set or the other, it doesn't really matter. Okay, so let's take a look at that square pulse again, and we'll use sinusoids instead of complex exponentials. So let's just focus on sinusoids. So if we took a look at that square pulse, we could see that it actually has odd symmetry. It's the dashed green line in this picture. It has odd symmetry, so it actually kind of lines up with a sine function to start with. So let's just use one term. Let's just use one sinusoid. And we need to find what coefficient to use here so that x1 is the best possible approximation to x that we could get. Well, what is that best choice? So we could choose anything, but the best choice is going to be the one that minimizes the error of the energy or the power in this error signal, which is x of t minus b1 sine omega naught t. Okay, since we're talking about periodic signals, we have to talk about power because they have infinite energy. So let's talk about power. So if we take a look at the expression for the power of this error signal, it's defined by this, and we can integrate over any period. We'll just go from 0 to t0, as that makes most sense. Okay, so if we take our definition of this error, x minus b1 sine omega naught, we get this expression here when we expand it out. And now, whenever we want to minimize something, what does that mean? Well, that means we take the derivative with respect to the thing we're trying to vary. In this case, we're varying b1, and we're trying to find the minimum with respect to b1. So we take the derivative with respect to b1 and set it equal to 0. So if you take that expression and take the derivative, then you end up with this. And we know that the integral of sine squared is just the the power in a sinusoid, and that's just t0 over 2. Sorry, if I have 1 over t0, then that's the power in the sinusoid. But we know that that integral is given by that. And then if we solve for b1, notice this is the only term that depends on b1. If we solve for b1, we come up with an expression that looks like that. And note that if we think back to the concept of inner product or dot product, this just looks like the projection of x onto sine omega naught t, or that first basis function. Okay, so for this particular case, what does that integration end up being? Well, if you take these two things and integrate them, you'll get 4a over pi. So that is the coefficient which gives us the smallest possible error with that basis function for approximating x of t. And if you take a look at the error signal, this is what it looks like. And that is the best we can get because we have minimized it. Okay, what if we approximate with 3 sinusoids? So we're going to take the original sinusoid, and then we know it has to be periodic signals and periodic with respect to t naught. So we're going to take 2 times the frequency and 3 times the frequency. In other words, we're going to take half the period and a third of the period of the original sinusoid. Or sorry, the original x of t, the original square pulse. And if you calculate those integrals for each of those, you'll see that the second term is actually 0, and the third term is 4 thirds a over pi. And if you add those sinusoids together with those coefficients, that's what it's going to look like. And the error signal is going to look like that. And again, we have minimized things, so this is the best we can possibly get with these basis functions. Okay, so what we've actually used there is the trigonometric Fourier series. So what is the trigonometric Fourier series? The idea with the trigonometric Fourier series is decompose any periodic signals with a sum of sinusoids. You've already taken a look at this, you already know of this expression. I'm just reminding you what it looks like. So we've got our basis functions are this cosine, this sine, and then we actually have a cos of 0 here, or the 0th frequency. That is another basis function. That's just a constant. And then these coefficients are found from projecting the signal, the periodic signal, onto each of the basis functions. The top equation is what's called the synthesis equation because it tells us how to build back up x of t by summing up the different components. The other ones are called the analysis equations because it tells us the coefficients. It tells us how to decompose the signal x of t into its components. Note that the a naught term is the frequency equals 0 component, and thus it represents, from a signal perspective, the DC component of the signal. In other words, just a constant offset. Okay, so how do we interpret that? Well, let's think back to just a very general form of decomposing any signal. If we have some basis functions phi, and we know how to take an inner product of f and take a projection onto phi, those phi are what's called the basis functions, and we know we can find the constants via a projection or an inner product. And again, you can think back to the vector analogy. We have a bunch of different basis vectors, and we find the constants by a projection. How about for Fourier? Well, for Fourier, our cosines and sines of increasing frequencies, integer multiples of the frequencies, are basis functions. And those coefficients, again, we're just finding those via projection or an inner product. And let's take a look at this from the information perspective again. Remember, what both the sender and receiver need to know are what basis functions are being used, so we're all on the same page, and we need to send the coefficients. For a Fourier series, when we're using trigonometric basis functions, the sender and receiver both need to know that we're using a Fourier series, so that tells us to use those trigonometric basis functions. And the information can be succinctly summarized as what coefficients go with what frequencies. Because the person at the other end of the line, or the thing at the other end of the line that's receiving the signal, he already knows we're using a Fourier series. If you tell them the fundamental period, that means they know what frequencies to use. And associated with each of those frequencies are the coefficients A and the coefficients B. That's the information that we need to send. Those frequency components, or the coefficients that go along with those frequency components, are integer multiples of the fundamental frequency, and from a terminology perspective, you'll hear this all the time. Those are referred to as the harmonics. So the fundamental is omega naught. The harmonics are 2 omega naught, 3 omega naught, 4 omega naught, etc. Okay, now let's think about this graphically. This is the way I like to think about it. Say we have x of t for which one period of the signal is a square pulse. So we can take a look at this from the time domain. So what I'm doing is that I'm taking a look at this 3D diagram from this viewpoint. So I'm looking at a 2D projection essentially, and it's time versus amplitude if I look along here. That is our time domain perspective of this signal. But I could just as easily look at it from this way. That is frequency versus amplitude. And I've flipped frequency here. So this is graphing the amplitude of the coefficients at those frequency components. So we have the first one, remember the second one was 0, third one was non-zero, etc. And this is just indicating that these are the what the components look like. This tells us how to scale those components. Okay? Okay, so now we have a time domain perspective of x of t, and we have the frequency domain perspective of x of t. It's important to note that both of these descriptions are equally valid. The information about x of t can be conveyed in either the time or frequency domain. And with infinite information from either domain, we can express x of t exactly. The frequency domain graph of x of t is usually called the spectrum or the frequency spectrum. So you hear that terminology as well. Now let's take a look at a musical analogy for that. Okay, so I'm hoping that the sound comes through the computer as well. So take a look at this where we, at the top we have a graph of the actual signal produced by hitting this key. Not sure if you heard that. Okay, well, if I start going up the keys, you can see that the signal is actually starting to get higher and higher in frequency. And in fact, that high C is actually the first harmonic of middle C. Okay, so those are individual components of a musical score. If I put several components together and play them at the same time, and I'm just going to choose some. Let's see. Yeah, okay. I'm just playing that over and over. So you'll see that we get this signal up above that is a composite signal, but it can be decomposed into its individual components. It could be just, how do I turn these off? Okay, so it's just that one, and that one, and that one. And if I put them all together, oh yeah, I gotta play them here. There, if I play them all together, then that's what I get. So that's one of the ways I like to think of what the Fourier series is doing, is that it's like playing a bunch of different notes at the same time. So if I'm playing a chord, then I'm effectively putting together a few sinusoidal signals and superimposing them on each other. And then if I change how heavy I hit the keys, then I'm changing the amplitude of a particular component. And it doesn't have to be a piano. I mean, it could be a guitar. When you play multiple strings together, you are effectively creating a composite signal with a bunch of different harmonics.